So Yann is a PhD student at the distributed computing group at the ETH Zurich, led by Vonlanthen. Yann is quite interested in the practical and theoretical aspects of blockchain, where he's looking into Ethereum as one of the main protocol, but he's also looking into other aspects. And he's also looking into decentralized governance and also aspects of proof of person. Yann, with that, the stage is yours.
Thanks for the introduction. Yeah, hey everyone, my name is Yann. I'm from ETH Zurich, and this is joint work with my co-authors Yoba, Juan, and Luciana. It says she's a doctor, she's a professor at Media Networks, and our advisor, Roger. So today I want to talk about vulnerability we found in Ethereum, and specifically I want to argue that we can de-anonymize validators, and why this is potentially a rather big problem for Ethereum. Right off the bat, we went through responsible disclosure, and if we got a bug bounty from Ethereum for that, and we got the written approval that we can now publicly share these results. So for Ethereum, I'm gonna stand here. Is this so as you know, Ethereum is made of a network of nodes. By nodes here, I mean computers that run the consensus lines. So for example, Lighthouse or Prism. And each node might potentially host validators. Validators are a completely different entity. I want to really emphasize this. It's a separate entity that should not be linked to nodes. And validators are actually the entities in charge of consensus, and each validator has to can sign attestation. Thank you very much. And each validator is identified by a unique ID. So I want to argue that it's important that these validators, they might be hosted by any of these nodes, but it's important that no one knows where exactly they are. And why exactly is it so important, right? So there's this network of nodes. The validators create blocks. So first, validator 7 will create a block, then validator 1, and validator 4 maybe. And let's say validator 1 got a huge reward for their block, maybe because of MEV, or some other rewards that they got. And validator 4 will see this, and if validator 4 knows where validator 1 is, and validator 4 is malicious, they can specifically target validator 1, right, with a denial of service attack, and thus prevent this block from validator 1 even reaching many nodes. And thus they can essentially erase this block from history, and they can pocket all the rewards themselves. So this is one thing that could go wrong if one knows where the validators are. There's other issues, right? You could keep doing this continuously, just always launch a denial of service on the proposer, and thus you might impact liveness. And there's other problems for further scalability improvements like time sharding or ADAS that actually needs even bigger privacy assumptions than what we are looking at here. So if this fails, you could also wonder, is the kind of follow-up going to work? Right? Let me first, to kind of give you an impression of what the attack looks like, I'll dive first into the Ethereum network layer. Probably not much talked about, but I think it's quite interesting. Yes, so we assume that there is, maybe I'll stand a bit to the side. Let's say this validator 3 wants to send a message, and by message here it could be anything, but most of the messages are attestations. So this is just kind of saying what the head of the chain is. And I mean, for our purpose, it's just enough to say a message. And this message should be broadcast to everyone. It's the simplest way. And of course, every validator has to send an attestation every epoch. And as you know, there's like more than 1 million of validators at the moment, right? So and an epoch is 6-7 minutes. So it makes a lot of messages that have to be sent around. And it's actually, I mean, there's many problems with it for scalability, but also even just the cost of running one of these nodes, right? If you run them and you have to pass by all the attestations, it actually costs real money. And so one solution, or the solution that Ethereum adopted, was to be based on gossip sub. And what gossip sub does is that it allows you to only care about a few topics. So instead of, messages are now going to be grouped into topics. Topics here in Ethereum, because in Ethereum they call subnets. So there will be 64 different subnets. And each validator only needs to care about some subnets, right? And in Ethereum it's defined as the default value is 2. So most validators are only in 2 different subnets. And that allows them to not have to care about most of the messages. So what happens now if this validator 1 wants to send a message that is actually destined for this subnet? It has been randomly assigned to that subnet. So it will find a peer, when one of the validator or this node's peer hopefully is in the subnet it is destined to, and this is the case. So here this message needs to go to subnet 5, so it will send it to this peer, and then this peer can able to propagate it inside this subnet. And so all the messages that are destined in that subnet will be propagated first only in that subnet, and then there will be specific validators that have the duty of aggregating these attestations, and then they will only send the attestations to everyone, right? So you can really improve message complexity that way. And our question here in this project was, but wait a second, doesn't this give away a lot of information, right? If you have these subnets, what are the implications for privacy here? So let's look at what a valid or a node might learn about its neighbors when it's connected to the network. So let's say this node, it knows who are their peers, and it knows their IP addresses. It also knows in which subnets these peers are, because that's like publicly advertised for the protocol to work. And then it also knows the messages that it receives from the different nodes. And so now we can ask the question, can we figure out what validators are hidden in these peers? And to do that, the kind of simple first step that we do is we tell all our peers we're interested in everything. Please send us everything, right? We can do that by saying we care about all subnets. And so we will receive a lot of messages. And we can now look a bit into detail what are these messages, or in which subnets are these messages coming from, right? And now we see this node here. It told us that it's subscribed to subnet 13 and subnet 14, and indeed we see a lot of messages from these two subnets. And that makes a lot of sense. But wait a second, we also see messages from different subnets that this node is not supposed to know about them, right? How is this node supposed to know? No one should send this node these messages. Right? So the most likely explanation, and then we can even go a little bit further, and we can check which validator has created these attestations, right? Which is the ID that has signed these. And in many cases, it might be pretty consistent. And in this case, all of them come from validator 93. So the most likely explanation is that actually this node is hosting validator 93. And so this is the whole intuition to this attack. So what do we do more specifically? We create a node that tries to have a lot of peers. It's connected to as many nodes as possible. So that when we tell them, yeah, we're interested in all subnets, we get hopefully a lot of messages, and we put them all in our book and we log all of them. And then this is for one of these peers. So I'm going to show you, let's say, just for one of these peers, what do we log? So here you see a plot over a given a few hours earlier this year, and you see the 64 different subnets. And these are all of these are attestations that we receive. And so you see that, let's say, all the red dots here are from a given validator, ending in 16. There's blue dots, validator 17, yellow dots 18, turquoise dots 19. And these kind of make up all of the little outlier dots, right? And then there's there's the rest, which you can clearly see this long line, which is the subnets that this node is actually subscribed to, right? And so that's why it knows a lot about these attestations. And then there's another kind of interesting pattern here, which are when this node subscribed to a different subnet. So here it's subscribed to maybe a subnet 30, just for a brief amount of time. And that's because it was on aggregator duty, where one of its validators that it was hosting had to do aggregation. So for a brief amount of time, it's like, hey, please send me all of these attestations. And this is pretty consistent because as you see at the end, it actually did send its own attestation and did that aggregation and then stopped caring about this subnet at all. So here we would say validator 16, 17, 18, and 19 are most likely hosted by this node. And so how do we want to, now we want to kind of do this not just for one node, but for more. So how do we do this? So we, based on the Prism client, we write a logging client, we call it Rainbow. And we run this Rainbow node in different locations. One of them is on our own servers in Zurich, and then on some other AWS servers as well. You see here how many peers that we get. I think it's actually quite interesting. So we try to have as many as possible, right? And the node in Virginia, in the US, gets the most peers. And then the one in Zurich is also quite good, probably because it's the best machine. And our node in Asia, ours is a little bit struggling. And overall, we get about 4,000. We get about 4,000 nodes that we connect to for some hours. And these are the ones that we'll now try to figure out which validators are hidden there. And so we run some heuristic approach based on what I told you before. We set some thresholds for what we deem to be high likelihoods, and we use this to deanonymize. And so I don't want to go into these specifics, but just show you some results. So just now for Zurich, there's 1,900 long connections that we make, so nodes that we connect to for long enough time. And out of these, we can deanonymize, or we can know which validators are hidden there for 58%. For 34%, we know for certain we think we know for certain that there's no validators there. For some of them, they're in all subnets, so we didn't even try. We think it's still possible. It's a little bit harder, but we didn't try there. And then there's the rest where we're not confident enough what's going on. But overall, we deanonymize 155,000 validators out of, at the time, there was slightly less than 1 million, so that's about 16%. And keep in mind, it was only 3 days and only 3 nodes, right? So we could run these for longer as well. Of course, we want to verify these results, see if that makes sense. We have three different metrics to verify this. The first is consistency. So we want to look for nodes that have more than one validators, which is most of them actually. We want to check, are these validators that we think are there, do they belong to the same staking pool? Do they have the same deposit address? Do they have the same fee recipient address? Doesn't really matter what this is. Or do they have consecutive IDs? So if like you saw the example, 16, 17, 18, 19, right? That means they were created right after each other. So it's a good hint as well that they were actually the same entity. So if this is happening, we say that it's consistent, and it's consistent for a lot of them. We check the uniqueness. So do we assign the same validator to different IP addresses? For most of them, it is unique. There's a few that are not unique, which we display here. And this is actually, I think, quite interesting. So whenever a validator, we think it's in multiple locations, we think it's a service provider. There exists a pretty well-known service provider that you can kind of subscribe to, and that service provider will kind of boost or like send your attestations from different places on Earth. And so we see where the service provider is operating and which the peers are from that service provider. And then we also check across, because we run different location, we check that the anonymization is consistent across the location. Here as well, we reach like 99% accuracy. Yeah, so some takeaways. Let's look at how many, maybe it's interesting to know how many validators are run in each peer, right? I told you a lot of them run multiple. We deanonymize quite a lot of small validators. So here is just the cumulative CDF. And a lot of them have actually quite a few. But you see there's like kind of spikes for 100, 300, 400, 500. There's always a little jump. So people like to run odd or like even numbers of validators on their peers. And then also you see for the staking pools, they run a lot more peers than the other providers. So there's up to, I think, yeah, multiple thousands is the biggest one, but yeah, many run like 500 or so validators per peer or per node. We can look at location. Here it's interesting that we de-anonymize better for validators that are close to us. So you'll see that the Zurich node is very good at de-anonymizing like Netherlands, Germany, Ireland, and Switzerland. And the Virginia node is better at de-anonymizing in the US. Yeah, it's actually quite interesting. There's a lot of nodes in the United States, but actually we see less validators in the United States, more in Europe. Maybe because our Zurich node was very good at staying connected. Then we look at organizations, so cloud providers. Yeah, there's the typical Hetzner, OVH, Amazon that you heard a lot about. Interestingly, validate in terms of, so these are the nodes, and then in terms of validators, we see a lot of them on Amazon and much less on Hetzner. So there's a lot of nodes on Hetzner, but somehow we don't find a lot of actual validators on Hetzner. That'd be also quite interesting. Yeah, so I don't want to go into. We also in our paper we talk a little bit about what you can do to prevent this, because I think we need to find solutions for this. I'm just gonna leave you with one simple like short-term idea, because I don't think there's like really the solution at the moment that exists on how to prevent this attack. But one way could be to that you use one node to propagate your attestations, right? And this can be de-anonymized. But then if you want to propose a block, you could use a different node, right? And that way, no one knows where the block is going to come from. And that's kind of prevents the most impactful attack. Yeah, that's it. I'm Yann. If you want to reach out to my socials, here they are. The paper is on archive. If you type the title of the presentation, you'll find the paper. Thanks a lot.
Thank you for presentation. I have a question about how difficult it is to do denial of service attack or for the node operator.
I don't know specifically. I would assume, I've just read blog posts about it, and people have said that it's quite feasible, but I'm not aware of any work that actually measures it and actually tries to do it.
What was the reason, thank you for the presentation, sorry. What was the reason why you are not able to detect the 7.5% arrest? Was it because you left to criticize yourself, or was it because something in the notes is not so clear?
Yeah, so we set, in order to say, okay, we de-anonymize it, we say, okay, we have to, maybe, we need to receive 90% of the attestations from the validator. And we set some heuristic thresholds, right? And we need to be 2 standard deviations away from the number of other validators and things like this, which means that for some validators, if we would lower these thresholds, we might say we're de-anonymized, but then we wouldn't be sure 100% then that we could de-anonymize them.
Yeah, the identity of validators being known ahead of time in the look ahead in Ethereum is reliable for aggregation of signatures and attestation. It's also reliable. It could be that you provide pre-confirmations without actually identifying the validator, but it's at the moment reliable as well for the proposal of pre-confirmation. So my question is, do you think that is reasonable, or for the sake of preventing attacks, the best solution is to just not know the identity of validators in advance?
Yeah, maybe I think one solution would be this secret leader election, for example, right? And then you would not know who will be the next proposer. And yeah, maybe this would be one of the solutions. But it only targets kind of one problem, or like one impact, right? And it only targets this attack, but we would still be able to de-anonymize kind of other things.
Yeah, also thank you for the presentation. I didn't really get if you just go the anonymized, like directly connected peers, or also like second tier validator peers.
You can start.
Yeah, only directly connected peers. So we need to be connected to this peer, and we need them to like us enough. So there's a peer scoring function. So I didn't go into this detail, but you only send information to a peer that you give a higher enough score to. So we need these peers to kind of think we're good peers, and there's multiple reasons why at some point your peer score can go down and then they don't send you actually 100% that stations anymore. Yeah, we need to be fully connected, and that's why if you run more than just the 3 nodes or 4 nodes that we run, you could deanonymize much more.
Okay, thank you very much. Yeah, again.